Yeah, good morning, everyone. Okay, so we will start. Okay, so last class we were discussing Bayesian maybe decision theory, especially maybe how a Bayesian rule can be used for maybe say classifying maybe a given feature vector. Okay, or maybe so that includes maybe either a single feature. Okay, actually we have seen with a single feature x. Okay, so based on probability, especially the posterior probability, so we will assign the class for which the posterior probability is largest. Okay, that particular class will be assigned to the so the given maybe the say input. Okay, vector. And then we have seen the concept of probability of error. So that means we are actually trying to minimize the error, okay, in classification. That is maybe our goal. So that also we have seen, and then we have defined what is our average probability of errors, etc. And then we have seen maybe why Bayes rule, okay, it will give the maybe the say the optimum, okay, error also, okay. So that also we have seen, and we have seen all these things. Now we will see. So there are two ways in which maybe we can see how these probabilities are actually come from. Okay, so that usually we when we discuss about maybe probability, we maybe say define a trial, okay, an experiment, okay, where we repeat maybe experiment say multiple times, okay, and then based on that we count the number of occurrences of a particular case, and then we define the probabilities. That is a maybe this I mean the relative frequency, okay, that is the frequencies that comes from the so that the experiments. But there is another way of maybe obtaining these probabilities that is actually based on the Bayesian maybe approach. So that is actually maybe based on, okay, some opinion, so that we will discuss later. But there are two ways in which these probabilities can be maybe obtained. So we'll come to maybe this discussion later, but just keep in mind. And similarly, we can have maybe say examples. Okay, so we are not going to the details. So that means if we want to maybe say find out or maybe apply this Bayesian decision for the classification, then we have to evaluate. We know that we have to evaluate the uh, I mean the these different probabilities. That is, we have to evaluate the class conditional probability or the likelihood. We have to evaluate it. Okay, and then we have to evaluate the prior probability. Okay, and maybe evidence we can maybe ignore. Okay, because uh, usually the p of x is actually common. Okay, because we have to change this but for different classes we have to find out. So that means that is going to be common. So that means we have to estimate these probabilities. Okay, from the given data we have to evaluate the likelihood and prior probabilities, and then multiply and then find out the posterior probability and then decide. Okay, so that is how this can be applied actually. Okay, and maybe that depends on maybe what is actually the data that is given, from where we have to evaluate these probabilities. Maybe we have to evaluate the prior probabilities. Okay, maybe from the given data set. Suppose for example there are a set of cards are actually there. Okay, and we would like to maybe say classify that into, okay, a price higher than say cards with greater than 50 k dollar. Okay, or price of that car is actually less than 50 k dollar. Okay, and that is going to be, say, suppose based on the height of the car. So that means if height of the car is actually maybe greater than a particular value, then we can say that that belongs to C1 class, and otherwise it belongs to C2 class or something like that. Okay, so but we are not going to the details of that problem, because that is easy to understand for any problem. Okay, but keep in mind that from the given data we have to find out maybe the prior probability, and then we have to find out maybe the class conditional probability or the likelihood. Okay, so that is actually the idea. And so these plots are actually showing maybe for two classes, that is for C1 and C2. Okay, they are actually in different maybe the colored histogram. So how we can actually maybe evaluate okay, maybe plot the distribution, okay, for different classes. Okay, and then maybe how maybe probability of x given Ci is actually maybe varying. Okay, so that is actually this plot, and then using that we have to evaluate the posterior probability. Okay, and then so that is actually, this is one case. Suppose we are given say x is equal to, maybe the height of the car is equal to, okay, in this case feature is height of the car, so x is equal to 1.0 is given, then we have to evaluate that for C1 and C2. So then, okay, so this is actually say point okay, 438. Similarly we have to evaluate for the other one and then look at which is larger. And so that is actually maybe we can plot that posterior probability also. Okay, so that is a maybe how we can apply this things. Okay, so far actually in this particular, so far discussed is actually with respect to one single feature. Okay, but we can always extend whatever the principles that we have actually studied, we can extend it to different scenarios or maybe more general scenarios. Okay, so that is actually the thing that we are now going to discuss. So that means we can always use okay, more than one, okay, features. So that means we can actually use a feature vector x actually. Okay, so that is one thing, so that is very important. Then we can have actually maybe more than two categories. So far we have seen, say, for example, W1 and W2. Okay, but that can always be maybe expanded to maybe a multi-class maybe problem. So that is W1, W2, W3. Okay, whatever it is the case. And then another possible way in which we can generalize whatever discussion that we have done is actually we can allow some actions. So for example, so far we have seen we are classifying it as W1 or W2. Okay, but we can say that in some cases, okay, for example, for a given x, suppose we reach a conclusion that it can belong to either W1 or W2, or there is a confusion that okay, it cannot belong to W1 or W2. So there are different such possibilities. Okay, so we can maybe allow actions actually. Okay, maybe other than just classifying it. So that means we can go for a rejection also. So okay, so that means it does not belong to a particular class. So in that way we can have a neutral decision also. So there are other actions we can maybe attach, okay, with our classification, maybe result, okay, which is actually not discussed so far. Okay, so that is it allow other actions, so that we will see, okay, later. Then we can have actually employ a more general, okay, error function. Okay, so in the previous maybe discussion, our maybe goal was actually to minimize the error. Okay, so probability of error is actually minimized, so that is actually based on the decision that we have actually taken. Okay, but we can always define maybe more better maybe a general error functions. Okay, that actually maybe takes care of maybe the different actions that we take. Okay, or maybe say for example, so far we have actually seen either classifying W1 or W2. Okay, a wrong classification actually cost equally, but there can be situations that one particular wrong classification can cost more cost, okay, compared to the other case. Okay, so that in that way we can actually bring in such a maybe priorities, or maybe a penalty, or maybe a cost, okay, on the maybe on the merit of the let's say the decision. Okay, so that is the case. So that means we can employ more general error functions, like a risk function that we will discuss. Okay, by associating a cost or a loss function with each error. So that means for each wrong action that we take, we can actually define maybe cost or loss. So these are some of the ways in which we can generalize it, so that this can be, okay, applied to any specific case or any general case. So that we will discuss, okay, one by one. Okay. So when it comes to maybe more than one maybe say variable, let us say that we are having a feature vector, okay, x, which is actually maybe an element of an Euclidean space r raised to d. So that means we assume that it's a d-dimensional, it is a d-dimensional okay feature vector. Okay. So D can be say 10 dimensions, so 20 dimensions, 100 dimensions, or even 1000 dimensions data can be there. So that is one way we are extending. And then we are assuming that the classes categories can be okay W1, W2, etc. up to say WC. So that means C number of classes. So you can also take different values. So when it takes a two, it's a very specific case of binary classification. Okay, maybe your special interest that we will see later. Okay, and so in vector notation, we can extend the base rule. Okay, maybe in vector notation, so just we are actually replacing that is in a small x with a capital bold X here. Nothing but that the single feature is actually replaced with a feature vector. So that is actually the difference here. Okay, all other the equations or the concepts, everything actually remains the same. Okay, so that is the case. And then assume that we define a finite set of actions. So that means whether it is accepted or it's a rejected or maybe say undefined, or so there are different possibilities in which we can define an action. So rather than maybe say simple accept or reject, you can have other actions also. So for example, maybe say if it is in a medical domain, suppose just take an example. So based on the decision we propose, okay, maybe this action, maybe say this action can be a prescription for a set of say medicine or a particular lab test or etc etc. So we are not simply saying that it is a positive or negative case, but you go for a set of actions. Okay, so based on the prediction, okay, that is actually done. So that means that depends on the problem, that depends on the how you're actually defining your okay maybe problems. Okay, so that is so okay, so that is actually the say the so suppose we define that we have alpha 1, alpha 2, alpha 3, etc to alpha L. So there are L actions. Okay, so that is again we are generalizing it. Okay, and then we define a loss function. Okay, here, so that is let us say that lambda is actually a loss function. So that loss function is actually defined in such a way that assume that you are given that Wj is actually the real the class. Okay, or maybe category. Okay, but we have actually taken an action of alpha I. Okay, so that is what is the cost associated with taking an action alpha I when the correct classification category is Wj. So that is a loss. So whenever you have a, say for example, let us assume that you are taking alpha j as the action, which is the correct action. Okay, and maybe your classification is also correct one. Okay, this category is Wj, you are taking the correct action, then you can say that the loss function is going to be 0. Okay, so it is a correct action that you are actually taking. So that means Wj, assume that alpha I represents okay predict the given feature vector x Wj. So then that is a correct prediction, correct action for the given feature vector, which is actually Wj. So in such case, we will not have a loss. Okay, otherwise we will have a loss associated with that particular action. So that means we can always maybe define what is going to be the penalty or so whatever value you assign for this lambda. Okay, so we anyway we define a loss function. So that is additional maybe so far we have discussed it. This is going to be an additional thing term that we are bringing in. Okay, and now based on this particular loss function, okay, we can define a conditional risk. Okay, so the risk is again maybe say associated with this loss. Okay, which is nothing but we define it as an expected loss. Okay, so that is on an average what is going to be the expected loss, which is a conditional risk. Okay, so so that means assume that we are given x as a feature vector and we take an action alpha I. Okay, so we take an action alpha I. Then we assume that okay the cost associated with taking the action alpha I, okay, I think this is the same thing. Okay, the definition of the loss function. Okay, and now how the conditional risk is actually defined is, okay, it's nothing but it's a conditional expected maybe loss. So that means we know that this is a loss, and when it comes to the expected loss, we have to bringing in that particular probability term also. Okay, so that the definition for conditional risk is actually, so we represent using R. Okay, and what is given is actually the feature vector x. For the given feature vector x, you are taking an action. Okay, so let us say ai or alpha I, whatever it is. Okay, so it is actually notationally there is some issue here, but assume that action is okay, ai or alpha I represents the same thing. It is nothing but, okay, we consider, okay, the summation over, okay, all the different classes. Okay, such that lambda of ai wj. So the wj is going to be constant here, because that is a sorry, wj is actually going to maybe vary for different classes. Okay, and what is given is actually the feature vector x. Okay, so that means for each so what is a class conditional, that is the likelihood. Okay, so that means you are given, okay, so sorry, this is not the class conditional, this is a the posterior probability. Okay, because you are given x, what is actually the probability that it corresponds to wj. So that is a this particular term. Okay, and then corresponding loss, what is a loss. Okay, so these two are multiplied together and summed it over for all the possible classes. So that is actually the definition for maybe the conditional risk. Okay, so this we can easily calculate, okay, for a given problem. So that is the idea, conditional risk. And we know that the risk is going to be, maybe we have to minimize it, that is expected loss has to be minimized. Okay, so now we can always define, maybe for a continuous case, we can always define for an overall risk. Okay, so that means suppose it's a general decision rule. Okay, so considering alpha 1 alpha 2. Okay, we are considering every x. Okay, then we know that we have to integrate it. Okay, so that means we are integrating, okay, the individual, okay, risks. Okay, the individual risks are going to be maybe say evaluated, and then we try to obtain the overall risk. Okay, so that is for every x, because x is going to be a feature vector on the d-dimensional space. So we have to consider all the possibilities. It is similar to what we defined for the base. Okay, what risk for the single attribute, or single feature. So here also we can see that if we are minimizing, because our aim is actually to minimize this individual, say for each x we are trying to minimize the risk. In such, if we follow that one, then this overall quantity will also be minimized. So that's why we can say that the optimus, the base rule is always returns a optimum. Okay, maybe case. Okay, so this is nothing but just an extension of the expression that we have seen for the single feature vector, a single feature. Okay, so it's nothing additional here, but only a feature vector. Okay, and the risk is actually the risk term is actually introduced. Okay, so that is a idea behind a loss function, and based on loss function we define the risk. Okay, and then we calculate the overall risk. Okay, and see whether which is the minimum. So that is here we define the set of actions also. So that is actually the concept of maybe overall risk. Okay, and so
Sorry,
we,
sir.
yeah,
Can you go to the previous formula?
this one, or
Yes, sir. So in the previous class, you defined the average probability error. The limit was from minus infinity to plus infinity.
yeah,
So is there?
yeah, here
So
actually,
here is
yeah, here actually we are actually defining maybe for the entire feature space. Okay,
yeah.
so that's why that integral is actually shown here. So because here actually not, we are not defining with respect to a single feature, but for the entire feature vector.
Okay, yes, got it.
Yeah, yeah, okay, so that is the case. Okay, so now now we have actually maybe okay, just whatever we have actually discussed is okay. So by base rule actually gives a minimum r. So because we are actually computing this for every alpha I and we are choosing the alpha I which is minimum. Okay, whatever we have discussed, and usually we will say that we use the notation star. Okay, especially to use the optimum value. Okay, so that's why we are trying to the r star here maybe the base risk, okay, which is optimum one is actually the minimum of maybe all the risk associated. Okay, so that is actually the notation wise how we can actually represent it. Earlier we have seen maybe say for example in curve fitting example we have seen w star, okay, where that was actually the optimum value of maybe the feature vector or the I mean the coefficient terms. Okay, so that is a star notation. Okay, anyway, that is the how the optimum value is actually represented. Okay, for a feature vector. Okay, or for a particular quantity. Okay, in machine learning terminology. And as I already mentioned, now we have a specific interesting problem because generally majority or maybe very interesting problem is actually a two category classification. Okay, so that is we will just see how this particular risk and other okay maybe terms okay can be evaluated or maybe how they are defined in this particular case. So assume that we have a whenever we have a two category classification, we have two classes, and so there are two decisions. So we can say two actions. So one action, let us say alpha one. So that is a decide W1. So that means you predict as W1. Okay, you are given okay X. Okay, then you are actually predicting it as W1. That is first action. Assume that another one is deciding W2, which is alpha 2. Okay, so here we have C is equal to 2. And so we can say that we have a shorthand, say representation, say lambda ij, okay, lambda ij, which is nothing but that is alpha, okay, sorry, lambda of alpha I given wj. Suppose we represent using the notation lambda ij. So where the original class is actually wj, okay, and the action that is taken is alpha I. So depending upon that alpha say action taken, so there will be a loss associated with it. Okay, so this is a conditional risk. Okay, maybe expression will look like we have a j is equal to 1 to c. So that means j is equal to 1 to 2 in this case, and lambda of okay a w j into p. Okay, this equation, and assume that okay. So using this particular notation, okay, bringing in here, we will get okay these two okay equations. Okay, so that is a so we have two actions a1 and a2, okay, or alpha 1 or alpha 2, whatever it is. Okay, because the slides I have okay taken from internet, so there is a notational difference, but doesn't make sense difference any. So here r of a1 given x and r of say risk associated with the a2 given x. So that means you are given x, what is the risk associated for taking an action a1 and risk associated for taking an action a2. So that can be just obtain, we can write lambda 1 1 into probability of w1 given x plus lambda 1 2. Okay, so because in one case we are assuming that on w2 w1 is a class, okay, and you are taking the action okay as a1. Okay, and other case we are assuming that w2 is a class and you are taking the action as a1. In the second case a2 is action taken, and in one case we are assuming w1 is a class, and in another case we are assuming that w2 is a class. So that is the way we can actually expand okay represent these equations okay in two cases. And then how we can actually maybe what is going to be the minimum risk decision rule. Okay, usually when we are having a classification problem, okay, okay, we have to define a decision rule. Okay, so based on this decision rule only we will be taking an action. Okay, or maybe a decision. So for example, we have seen that with respect to posterior probability, or in the case of base decision rule we have already seen. So similarly maybe here we are interested in with respect to risk, we are actually maybe defining the decision rule. Okay, so assume that we have w1, we are deciding w1 if the risk associated for a1 given x is actually less than risk associated with a2 given x. Otherwise, we decided as w2. I think easy to understand. It's similar to because the risk is actually wherever the risk is actually less for a particular action. Then correspondingly we will decide which class or which category it belongs to. We have already defined that a1 is actually the action corresponding to deciding w1, and a2 is actually the action so that decides w2. So that is the case. In another way, maybe using the previous equation, we can maybe rewrite this the above decision rule in this fashion. That means rearranging these two equations. So that is lambda 21 minus lambda 11 in the probability of w1 given x greater than lambda 12 minus lambda 22 in the probability of w2 given x. So that means the risk is actually replaced by maybe this particular equation. Sorry, the terms maybe from this equation. So that is another way you can try to see whether that is correct here. So that is another way. The same decision rule we can express in another terms. And another interesting way in which we can represent this is actually using a likelihood ratio. It's also maybe just continuation of the same previous discussion. And we know that what are actually the likelihood decisions, that is the probability of x given w1 and the probability of x given w2. So that's a likelihood ratio we have already seen. What is a likelihood? And now the ratio of the two likelihoods. And this can also be, we can obtain this from this equation. Maybe combining with the other results. We can replace maybe this particular posterior probability with maybe the results that we have already seen, and you can obtain this equation also. So that is the way how we can actually maybe represent the two category cases. And the decision rule we can be defined in different forms. Each of them may be interesting in particular scenarios. And here we assume that we'll have a threshold. Usually likelihood ratio is going to be the ratio of maybe probabilities. So we'll have a threshold value, and that is actually defined by maybe this particular term. So that is a maybe another way in which we can actually express the decision rule. And this is a special case where assume that our the loss function is defined as something like this one. That is whenever we have whenever we have wj and alpha I where we have the correct prediction comes, we have a loss is 0. Otherwise we have a loss found 1. So that is a typical maybe 0 1 loss function. So we are defining the loss to be either 0 or 1. So that is actually the loss function here. So in that case we can substitute these values into maybe our previous equations in this equations. And maybe we can maybe simplify or maybe we can rewrite the risk equations in this particular form. Because there we know that lambda 11, lambda 12, lambda 21 and lambda 22 can take either 0 or 1. So these equations, maybe this particular equations, we can substitute corresponding lambda values based on this 0 1 maybe definition. So we can have this result. So that also you can check. Maybe the other terms will vanish because they are going to be lambda values are going to be either 0 or 1. So some of the terms will be vanishing, and some of them will be the probability values alone. So that is the probability of w j given x only the remaining cases. So that is why we are having only this term in this particular equation. So this is maybe a typical 0 1 loss function, but we can have can define other loss functions maybe defined. Maybe you can bring in more number of maybe actions, more number of classes. All these are actually work easily we can extend it the techniques or the principles into in general cases also. So similarly the decision rule that we have seen can also be maybe the terms of, okay, this is a risk, okay, the first equation in terms of the risk, and maybe, okay, this is going to be with respect to the probability, okay, and okay, this is another one, okay, so that these are actually the base, and then the likelihood also you can actually define, and okay, we can see what is going to be the decision rule in such cases. Okay, so this is actually maybe how this but zero one loss function actually works. Okay, and say maybe generally about maybe I mean generalizing the Bayesian case for a feature vector. Okay, so this is also another example. Okay, so we are not going to the details, but you can, it is straight away we are just calculating these values, okay, and then maybe substituting in these equations to make a decision. Nothing, no other additional maybe concepts are actually, or maybe studies are required, but just finding out the probability values, and maybe defining this, okay, but this particular I mean the loss functions, and then deciding it. Okay, so that is actually maybe about maybe in general about the Bayesian decision rule. So what we will go is we will continue with the next class. Okay, so we will see another very important concept like okay, decision discriminant functions. Okay, and maybe how we can actually define the discriminant functions, maybe in the context of maybe Bayesian decision rule, especially how so how we can actually define discriminant functions for the with respect to Bayesian decision rule, and how that is actually maybe can help us to make a decision, okay, or in pattern classification problem. So that is actually what we will be discussing, say, tomorrow. Okay, so today we will wind up with okay, this one. Okay, so thank you, and we will continue from tomorrow.